Hi, in this video we are going to talk about coloring problem. So let's get started. What is this coloring problem? It is very hard, so it is a so-called NP-complete problem. And the problem itself is that coloring the vertices of a graph such that no two adjacent vertices share the same color. This is called a vertex coloring. And this algorithm reached popularity with the general public in the form of the popular number puzzle Sudoku. The smallest number of colors needed to color a graph G is called its chromatic number. There may be more than one solution, it's very important. For example, we can color a graph with 4 vertices in 12 ways with 3 colors. But there's lots of application of graph coloring. For example, bipartite graphs. Determining if a graph can be colored with 2 colors is equivalent to determining whether or not the graph is bipartite or not, and thus computable in linear time using breadth-first search. Bipartite graph is a graph whose vertices can be divided into 2 disjoint sets U and V. U and V are independent sets such that every edge connects a vertex in U to one in V. So this is the first application. The second is making schedules. For example, we want to make an exam schedule for a university, and we have different subjects and different students enrolled on every subject. Many subjects would have common students, of course, and the problem is how do we schedule the exam so that no 2 exams with a common student are scheduled at the same time, and how many minimum time slots are needed to schedule all exams. And I think it's pretty counterintuitive because you may guess that map coloring has nothing to do with these kinds of problems, but it is. So this problem can be represented as a graph where every vertex is a subject and an edge between 2 vertices means there is a common student. So this is a graph coloring problem where minimum number of time slots is equal to the chromatic number of the graph. Another very important application is the radio frequency assignment problem. When frequencies are assigned to towers, frequencies assigned to all towers at the same location must be different because of the interference. And how to assign frequencies with these constraints, and what is the minimum number of frequencies needed? This problem is also an instance of graph coloring problem where every tower represents a vertex and an edge between 2 towers represents that they are in the range of each other. Of course, register allocation is a difficult problem. In compiler optimization for software engineering and so on, register allocation is the process of assigning a large number of target program variables onto a small number of CPU registers. And this problem can be solved with the help of map coloring. And of course, the map coloring is the typical problem of coloring problems. So we want to construct a map of countries or states where adjacent countries or states cannot be assigned the same color. This is the typical coloring problem, by the way, yes. And there's the 4-color theorem that states that 4 colors are sufficient to color any map. So this is the so-called map coloring problem, very famous. There are several solutions for the coloring problem, and one of them is the greedy solution. The problem is an NP-complete one, as we have discussed. So sometimes we just want to get an approximate solution. It is quite common for very hard problems. For example, the traveling salesman problem is another problem that's very hard to find the exact solution. So we just want to get an approximate one. And this is what's called heuristics, that we don't want to find the exact solution. We are looking for just some pretty close solution. Greedy algorithm considers the vertices of the graph in sequence and assigns each vertex its first available color. This is why it's greedy. It's going to go in a sequential basis, and if there's an available color, it is going to assign it. It doesn't guarantee to use minimum colors, but it guarantees an upper bound on the number of colors. The basic algorithm never uses more than d+1 colors, where d is the maximum degree of vertices in the given graph, or the branching factor. The degree is just the number of edges coming out from a given vertex. So let's see an illustration of the greedy one. We start at node 1, and for example the first color is blue. Usually that's why we use chromatic numbers and we don't use RGB colors, for example blue, red and so on, but instead of these colors we use the chromatic numbers 0, 1, 2 and so on. So this is the first chromatic number, whatever. Then we go to the second one and we assign a different color because they are adjacent to each other. Then go to the third node and we come to the conclusion that we can reuse the first color. Then go to the fourth node and we are going to use another color. Then we go to the, and as you guess, if it wasn't a greedy solution, greedy approximation, then we can reuse the red. But because it is greedy, it is going to assign yellow. Okay, so it is red, and we can reuse the color blue. So we used 3 different colors with the greedy solution, but we may come to the conclusion that 2 colors will be sufficient. But it's a greedy solution. It is okay, it is working fine, but it is not the optimal one. The Walsh-Powell algorithm is a sophisticated one. It performs better usually than the greedy solution. It uses a heuristic. We should eliminate the nodes with highest valence, with highest degrees as soon as possible. So the algorithm is as follows. Find the degree distribution or the valence for the nodes. Sort in descending numerical order by valence or the degree distribution. They are synonyms. We can do it in n log n time complexity with the help, for example, merge sort. Then color the first vertex with highest valence with color chromatic number 1. Then iterate through the list and color every vertex not connected to the colored vertices with the same color, so the chromatic number 1 again. Cross out all colored vertices from the list and repeat until there are no uncolored vertices left. So we have a graph like this. We calculate the frequency or degree distribution or valence for each of the vertices. And we come to the conclusion that A has a frequency 2 because it has 2 edges. C, for example, has 4 frequency because it has 4 edges. So we sort it according to the frequency. And we start with the vertex that has the most frequency, so 4. And we are going to assign the first number, the first chromatic number or first color to this vertex because we can eliminate the vertex that has the most neighbors, and it's very good. We iterate through the list and try to find any other vertex where we could reuse our colors. And of course we are not able to use the blue for A, B, D and E because they are adjacent to C, but the F is good. We can reuse the color blue. Then we cross out these vertex C and vertex F from our list and we go to the next one. And of course we start with the highest frequency because the next highest frequency is E. We start with it. We assign a chromatic number, or now a color, red, and we try to find another vertex. So we iterate through the list. For example, the A is a good one. We can assign red for the A because it's not adjacent to E. Then the next one will be B according to our frequency vertex list. So we assign the third color. It is yellow now. And we try to find another vertex where we can reuse our color. And we come to the conclusion that D is not adjacent to B, so we can reuse our yellow color. So this is how this Walsh-Powell algorithm works. We have to find the degree distributions or valence. We have to sort it. We can do it very quickly. And then we can assign numbers according to these frequencies. And of course we have to make sure that we are able to reuse the color as often as possible. And of course the backtracking is another solution. We assign colors one by one to different vertices starting from the first vertex. The first vertex is optional, of course. Before assigning a color, we check for safety by considering already assigned colors to the adjacent vertices. And if we find a color assignment which is feasible, then we mark the color assignment as part of the solution. If we do not find color due to clashes, then we backtrack. And this is why it's kind of a backtracking. And as we have discussed for N-Queen's problem and so on, another solution would be to build a search tree and use depth first search. And in depth first search, where we go to the leaf, which is not a good solution, we keep backtracking. So we are going to use recursion again. Thanks for watching.